Okay, this is for online students. Although you can also access the recordings when they come. Okay, so that didn't work. Fine. All right. On to indices and logarithms. How to evaluate logarithms in simple cases. So you can do logarithms in your head when they're simple. And then how to use the rules of logarithms to solve equations where the unknown occurs as a power. So where the unknown x is the power of something. And you need to use, you have to know how to use logarithms. All right, let's jump in. How, if you were reading this on your own, this is, by the way, these textbooks, they're meant to be read by students. They're not, I mean, I'm using it also for class. But you can also read through the textbook yourselves. Are you having trouble seeing it? No. You don't like your script. Can you read okay? Okay. No, I gotta sit closer. Sorry? Yeah, but fine. So come sit closer to the middle. Come sit there. Okay. So you said that you've all seen this before, so this should be more of a review, so we can go a bit more quickly. So one, you know what exponents are and what they mean, right? An exponent, when it's a simple positive number, what it means is I multiply the base. Here they're using b because b is the base, by the number of times that is in the exponent. So b squared is b times b. B cubed is b to the third power is b times b times b, and so on. We're comfortable with that. So stop me anytime you're like, wait, what, oh, what? Just stop. Okay? So that's fine. Now, how do we handle negative powers? We know how to do 2 to the 1 power is 2. 2 to the power 2 is 2 times 2, 4. 2 to the power 3 is 2 times 2 times 2, which is 8. 2 to the 4th power is 16, and so on. So we can see the pattern multiplied by 2 every time, right? So now what happens if you want to go in the other direction? When the exponents are getting smaller, and they become 0 minus 1 minus 2 minus 3, what is it then? Anybody? Remember? Do you know?
2 to the power 0 is 1.
Okay. power 0 equals 1. Okay? How about 2 to the power minus 1? Do you know what that is?
What? Half or 1.
Okay. I'm not sure about this. Okay. Have you seen this before?
Yes.
Yeah? Okay. How about that? What would this be? 2 to the power minus 2. Quarter? Did you do that? Okay. How did you say a quarter? How do you get a quarter? Explain to us your thing.
I just said it goes off that.
Keep going. You're on the right track. You're on the right track. It is a quarter, you're right. Why is it a quarter? It is a quarter.
It's 1 over 2 or 2.
So we'll come back. So what Justin just said is 2 to the power negative 1, for example, is 1 over 2 to the power 1. This is 1 over 2 to the power 2, and so forth. I usually run the right one with these little tails. Now, so then what would 2 to the minus 3 be? If we follow the same pattern.
1 over 8.
Over 8. Right. 1 over 8. That's 2 to the minus 3. And we could keep going. So, you notice when the powers are going up by 1, we are multiplying by the base. Right? 2 times 2 is 4, times 2 is 8, times 2 is 16. When the powers are getting smaller, we're subtracting 1. So we divide by the base. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. This one, you. I don't know why it's not right. The base to the power 0 is 1. And it is always 1.
And
Any number. With the exception of 0. 0 to the power 0, we don't know what that is. Math does not know what 0 to the power 0. Any other number, positive, negative, fraction, decimal, I don't care. Any other number to the power 0 is 1. Is it equal to 0? No, it's equal to 1. Anything to the power 0 is equal to 1. Now, why is that true? You have to understand. It's not enough to just accept because Nanya said so. No, not because Nanya said so. Because we follow the pattern, right? So we have 2 to the... Suppose now, instead of 2, we did 3. So 3 squared is what? 3 to the power 1 is what? 3. So we divided by 3. So 3 to the power 1 is the same number, 3. To the power 0 is you divide by that number, right? So you're always, whenever you have a to the power 1, is always a. A to the power 0 is a to the power 1 divided by a, which is a divided by a which is 1. Right? That's 1. Try that again. So a to the 0. Just like any number here, if we have a to the power 3 equals a to the power 4 divided by a. Is this true?
Yes.
Yes. So a to the power 0 is a to the power 1 divided by a, which is just a over a, and anything divided by itself is always 1. Doesn't matter what the number is. This could be a negative number, it could be a very big number, a very small number, a very long decimal number, it could be pi, doesn't matter. Number divided by itself is 1. With the exception of 0. If you have 0 divided by 0, then we don't know what this is. 0 divided by 0 is not 1. It's undefined. So this one is undefined. We don't know 0 to the power 0. But any other number, so long as a is not 0, that number to the power 0 is 1. Right? Now, we can follow the same rule, the same pattern, to get to the negative powers. So we say, well, if the way to get the negative power is to divide by the number, then here again I divide by the number 2. So 1 divided by 2 is a half. And a half divided by 2 is a quarter. And a quarter divided by 2 is 1/8. And so forth.
So how do we change? To replace that quarter with the s constant.
To be what? To be this? 2 to the power negative 2.
Because there's some equation that we index.
Inverse it. I'm not sure. I don't follow what you mean.
I mean, some equation I thought it index. It is like quarter, but we need to replace it to be 2 by this. So I thought we replace.
Did you write what you're thinking? I'm not quite following. The blue one isn't very good. You can try. Maybe let's use this part of the board here. Let's see if it works over here. I don't know why sometimes some parts of the board work better than others. 2 to the x. That's logarithms. That's not negative powers. That's logarithms. We're going to get there. Keep that in mind. Now I see what you mean. So if the unknown x is the exponent, then how do I find x? Well, that's the logarithms. We're not at logarithms yet. We're at negative terms. So you just continue the pattern. So when you have a negative power, notice the number is not negative, right? The exponent is negative, but the number is not negative. But what happens when you have a negative exponent is it's the same as, so 2 to the minus 2 is the same as 1 divided by 2 to the power 2. Yeah? Does that make sense?
Yes.
Okay. So test. What would be this? 1 over 2 to the minus 1. It's London defined it very nicely. Here, come in.
Go.
Try. You're here to learn. Listen, I think I told you last class. You are going to make mistakes. All the predictable. You're here to learn because you don't know.
I wasn't there.
You try. But learning is, you have to think, what do I think it is? And then I can help adjust the thinking. It's helpful if you say out loud what you're thinking, and then others can add or. So this is he is not doing this by himself. The class, we are doing this. It just happens to be the understanding of the marker, right? So 1 over -2. Okay, that's the first attempt. Let's see if we can refine it. Let's see if we can refine this. Divide, you multiply it by the inverse of this, right?
Yes.
So 1 over 1 times, now we invert the half, so it's 2 over 1. 1 times 2 times 1 over 1 times 1 is 2 over 1, which is 2. So the answer is 2. Another one. Let's do 1 over 3 squared, 3 to the minus 2. Very nice, minus 2. Everybody, think about it and write down no phones, put your phone away. No calculators, put your phone away. Calculus does not require calculators. Calculus does not require calculators. Calculus is about your head, not about your business. So what is 1 over 3 to the power negative 2? Let's do a few. Do some quick practice. One, 3 to the 2 equals what? 4 squared over 4 1 equals what? 5 to the power 1 divided by 5 to the power negative 1 equals what? And 2 squared times 2 to the minus 3. Four problems. There are 4 problems on the board. A, B, C, D. Try to work out what each of these would be. I'm going to add one more. No calculators. 7 to 3 to the power 0. Minus 2 to the power minus 2. We're going to talk about negative numbers. Minus 2 to the power minus 2. To the power of negative. I'll stop.
D. Which one?
2 squared times 2 to the power negative 3.
You read D.
2 squared, 2 to the power 2 times 2 to the power negative 3.
E times or point.
No, E is just the A, B, C, D, E. So 1.723 to the power 0. This is just a decimal number. Done? Almost all right. Check E. Sorry, not E. Which one? Yeah, E is F, I meant. Check F. Mm-hmm. 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 Mm-mm. Everybody's getting F wrong. So we'll have to review that one. D is right, C is right, E is right, B is right, A? No. A is not right. And F is not right. Okay. Did everybody finish all of them? 9, 4, 25. Good so far? F? No. 2 squared to the power 2 to the power 2 times 2 to the power minus 3. Times. But dot means times. It's a faster way of, instead of writing x, also because x is a variable, So it might cause confusion. So now that we have the variable x, instead of saying multiply with the x, we say multiply with a dot. That's wrong, yeah. Okay, so let's do them together. 1 over 3 to the power minus 2 is 1 over, no, 3 to the power negative 2 is 1 over 3 squared, which is 9. Sorry, the marker is running out here. I don't know what to do about it. I don't have a better marker. 1 over a ninth. Yeah? 3 squared is 9, right? So 1, it's not 1 over 9, it's 1 over 9, so it's 9. I think everybody got that. Very good. This one, 4 squared is 16, divided by 4 to the 1 is 4, so the answer is 4. Everybody got that. Here, 5 to the power 1 is 5, divided by 5 to the power negative 1 is 1/5. And when you multiply it up top, you get 5 times 5, which is 25. I think everybody got that. So it's a bit squished here. Here we have 2 squared, which is 4, times 2 to the minus 3 is 1 over 2 to the 3, which is 8. 4 times 1 over 8 is a half. And then some number to the power 0 is 1. Everybody got that? Now, the tricky one. So let's get rid of these guys. So this is good. You've understood, you can apply the basic rules of powers. So now we have a negative number multiplied to the power negative 2. So let's start with, if I have minus 2 to the power 2, what does this mean? Minus 2 times minus 2, which is, I heard, 4. Not negative 4? No. Okay. Because it's squared, so we have a even number of negative signs. Whenever you're multiplying an even number of negative signs, every negative sign is paired with another one, and so the result is positive. Yeah? So now, let's use this to think, what about if the exponent, all I change is I make the exponent negative. So that means it's 1 over minus 2 squared. Everything in the bracket is this power. It's not just the 2 that is to the power minus 2, minus 2 to the power minus 2. Right? So now we have 1 over minus 2 squared is the same thing. We know what that is. So it's a quarter.
How would that?
Huh?
How would that?
Yeah.
So you said it's zero. Why I get it?
It was negative. You wrote negative a quarter. And it's not negative a quarter. It's positive a quarter. This is important. No, you can't get a negative sign wrong. Math doesn't play like that. You have to know where the signs go. So now let's see, what would be minus 2 to the power 3? Minus 2 to the power 3. So let's remind ourselves, what would be 2 to the power 3? Positive 2 to the power 3 is what? 8. 2 times 2 times 2 is 8. So what is minus 2 to the power 3? Negative 8. Minus 2 times minus 2 times minus 2 is minus 8. So what would be minus 2 to the power minus 3? Charles, what do you think? Minus 2 to the power minus 3. Okay, 1 over 8 is a guess. What's your guess? 1 over negative 8. And by convention, we put the negative on top. So minus 1 over 8. Correct. Because this is the same as 1 over minus 2 cubed. So it's 1 over minus 2 times minus 2 times minus 2. Put the brackets. And we have 3 minuses, so we get a negative number. 2 times 2 times 2 is 8, so negative number with the 8. Yeah? I have another fun one for you. What is negative 1, very simple number. Actually, sorry, before negative 1. What is 1 to the power 10?
It's
1 times 1 times 1 times 1, 10 times. 1. How about 1 to the power 1,000? 1. Okay, how about 1 to the power minus 3? Huh? 1 to the power negative 3 is the same as 1 over 1 to the power 3. What is 1 to the power 3? 1. 1 divided by 1? 1. Oh, boring. 1 to the power negative 3 is still 1. How about to the power negative 300? What will it be? Thank you. What is 1 to the power negative 300? 1. Let's write it again here. 1 over 1 to the power 300 is still 1. So really, it doesn't matter what power we have for 1. The answer is always 1. So 1 is, when you multiply 1 by itself, you can multiply it by itself as many times as you like, it's still 1. Huh? Come again? So we asked, what is 1 to the power minus 300? That's the same as 1 over 1 to the power 300. And we said when you have 1 to any power, it's still 1. This is 1 times 1 times 1 times 1, and you can multiply 1,000 times, you still get 1.
1 is a base.
Yeah.
1 is a base. So if power of the base is 1, 4.
The base is 1, raised to a power. So 1.
Base to the power 100. Is what? No. 100.
Can you explain? If you have 1, let me write this now with a brighter marker. 1 to the power 1,000 equals, we said it equals 1. Can you explain why? So let's start. 1 squared is what? 1 times 1, 1. What is 1 cubed? 1 to the 4th. And you can keep going forever. I can have 1 to the power 1,000,000. Still 1. And then if it's a negative power, you're just dividing by 1. So it's still 1. Now we make it more interesting. What is negative 1 to the power 99? One minus one. Okay. How can we think about this? Math is about how you think about a problem. So you look at this and you go, "Ooh, I have to multiply it 99 times. That's a lot of work." Is there a trick? Is there a logic I can use? How do you get minus 1? You guessed. Guessing is not allowed. So we can say, well, let me see if I can find a pattern, right? That if I have negative 1 to the power 1, that's minus 1. Negative 1 squared is what? 1. Negative 1 cubed is what? Minus 1. Negative 1 to the 4th is what? 1. Negative 1, this is the last one, to the power 5, minus 1. Every time we go up 1 power, we multiply by minus 1. So we get a minus 1, a plus 1, a minus 1, a plus 1, a minus 1, a plus 1. Ah, there's a pattern. And can you know, now if I say 99, which one will it be? 1 or negative 1? Why? Say it louder, Charles.
I think it's because 99 is an even number. I can see the pattern there. We use the power, which is the prime number.
You have the right idea, but your terminology is a bit... So this is a odd number. Odd numbers are, there's odd and even. Even is divisible by 2 with no remainder. Odd number is you have to divide by 2 and then there's a 1 left over. Right? So 3, if I divide by 2, or I have to subtract, if I divide by 2, there's a 1 left over, well, a half, I guess. 2 divided by 2 is a whole number. So even is if I divide by 2, I get a whole number. Yeah, this makes more sense. Odd, if I divide by 2, I get a fraction, right? Not a whole number. So 2, 4, 6, 8, 10, those are even numbers. 1, 3, 5, 7, 9 are odd numbers, and the pattern continues forever. So 99 is a what? Even or odd number? Odd number. And the odd powers, what value are they? Negative 1. So by logic, I can claim this is negative 1. Now, what would be negative 1 to the power 100? 1. You see the power of math. When you find the pattern, you don't have to do the whole calculation. You can see, I know if it's true here, it will always be true. What about if I put a negative sign?
One explanation of 9 is 1.
We'll see. Which one? So what is negative 1 to the power negative 99? Still negative 1. And this is negative 1 to the power negative 100 is 1. So it's the same as 1 to the power 100. Sorry, negative. It's the same as negative 1 to the power 100, which is 1. 1 over 1 is still 1. So whether the negative sign is on the bottom, here I can write the intermediate step. 1 over negative 1 to the power 99 is 1 over negative 1, which is negative 1. So the negative doesn't care if it's on the top or the bottom. So all that matters is the... Now, do you know whether these numbers are even or odd? Are these, is minus 9, we said 99 is an odd number. What about minus 99? Is it even or odd? Odd. And minus 100 is even. Right? If you think of a number line, there's 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 1 divided by 2 is a half. 2 divided by 2 is 1. That's a whole number. 4 divided by 2 is 2. That's a whole number. So these are even, even. This is odd, odd. 0. Is 0 even or odd? Is 0 even or odd? It's one of them. It's even. If you divide by 2, you get 0, which is a whole number. So this is even. Now minus 1. Minus 1 divided by 2 is negative a half. That's not a whole number. So that's odd. Negative 2 divided by 2 is minus 1. Minus 1 is a whole number. So that's even. And the pattern continues. Even, odd, even, odd. So if 0 is even, 1 or minus 1 is odd. 2 or minus 2 is even. 3 minus 3, odd. 4 minus 4, even. So the sign doesn't actually make a difference to being even or odd. You also mentioned prime numbers. We're not going to work with prime numbers, but just so we're clear about what they mean, what is a prime number? A number that is only divisible by 1 and itself. What are some examples of prime numbers? 2. Mike, what's a prime number? An example of a prime number. 5. 3. 11. 7. 22. Can 22 be divided by any number besides 1 in itself? No. Okay. $13. That's the next prime number. There's a fun, this is not calculus, but we have 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 is a prime number. 20, 21, 22, 23 is a prime number. 24, 25, 26, 27, 28, 29 is a prime number. 31 is a prime number. And you notice something fun. This is a pair, right? First of all, prime numbers will always be even or odd? Prime numbers, they're always odd. Because if it's an even number, it can be divided by 2. And that makes it not prime. So all prime numbers are odd. So there's a pair, 17 and 19 are a pair, 29 and 31 are a pair. 23 is not a pair, it's by itself. As we keep going up, there is a question in math, and nobody knows the answer. So we know that there are primes as big as you can go. There's no limit to how many primes you can find. There are infinitely many primes. They get very big and very rare, but they come. But even more interesting is, will you always find pairs of primes? As you get to bigger and bigger numbers, like numbers with 100 digits, computers have to calculate these numbers. Do you still find pairs of primes? This is an open question in mathematics. If you can solve it, you will be world famous. People for hundreds of years, the best mathematicians in the world, have tried to answer the question, if you keep going forever, will you always find more pairs of primes? Or at some point, the pairs stop. The primes continue, but they become like by themselves. And that's the question. All right, so those are prime numbers. So we should review the rules of powers. You have to know how to manipulate powers. So now we said, okay, if b, we know what b to the n is b times b times b times b n times. So obviously if it's 2, then it'll be just b times b. But we get the idea, right? B to the 0 is what? 1. B to the negative n is 1 over b to the n. Now we want to ask, what happens if I multiply 2 powers together? What if I have b to the n times b to the m, a different number? What do I get? So this is the same base. So like 2 squared times 2 to the power 3. Bn plus m. So if I have 2 squared times 2 cubed, that's 2 times 2 times 2 times 2 times 2, which is 2 to the 5, which is the same as 2 to the power 2 plus 3. So when you have 2 powers multiplied together, this doesn't work if they're added together. Yeah? 2 squared plus 2 cubed is 4 plus 8, 12, right? It's not, there's no formula for this. This is just what it is. Yeah? But when they're multiplied, you do this. Now, what about b to the power n divided by b to the power m? I gave you an example of this already. So now, here we multiplied the 2 powers. Now we're dividing the 2 powers. B to the power n minus m. Yeah? And in fact, these two are kind of the same rule, actually. Because we could say, we know this, right? So if I had b to the n times 1 over b to the m, which is the same thing as this, right? Yeah? We agree? This is the same as this? Ishmael? B to the n divided by b to the m is the same as b to the n times 1 over b to the m.
Yes.
Yeah? Okay? And we know what this is. We can write it like that, right? So we can write b to the n times b to the minus m. Yeah? And we know this rule. If I multiply two things, I just add their powers, right? So I have b to the n plus negative m, and therefore it's b to the n minus m. So actually, these two rules are kind of the same rule, actually. Okay? And that's basically it. Let's just check our understanding. If I give you a base a to the power n times another number b to the power n, does this simplify to anything? So for example, if I say 4 squared times 3 squared, does that simplify to something? Can I use this rule? No, because they are not the same base. Is there any simplification I can do? Yeah? What?
I think we can solve 4 like like 4 square on its own and 3 square on its own, and then
Yeah, we can, I mean, here I have actual numbers. This is 16 times 9, which is 90 and 54, 144. But I want to know, as a general, is there a rule of what I can do with this? So I'm going to suggest the rule is AB, I don't even need that, to the power n. The product of the powers, if they're the same power, is the power of the products. Now, why is this true? We can demonstrate. So let's say we have a squared, b squared. So we can go, well, this is a times b times b, right? Everybody agrees? Okay. I'm just going to rearrange this. I'm allowed to rearrange a product, yeah? It doesn't change the value. So I'm going to write a times b times a times b. Are these the same? Charles, are you with us? Is this equal to this? Yes. No? Why no?
It's a times b. That is a b.
This is a times b times b. So there's two a's and two b's. And here I just swapped the a and the b. I took these two and I swapped them around. Why not?
You multiply a times b, it's a b. A times a is a square.
Yeah. But now I have all of them together. A squared times b squared. I have all of them here. Yeah?
Okay.
Am I allowed to do this? B times a times a? Is this equal to b squared, a squared? Is that true?
Yes.
Okay. So I am allowed to move them around. Yeah? Okay. So when you have things multiplied together, you're allowed to rearrange the product. So I can write this. Now, what is this? This is A, I can put brackets around them, which then I say, well, that's just AB twice. Now I have proof, because I didn't put specific numbers. This is true for any number A and any number B. And you can check it if you want to make sure. But this is the proof. Very simple. So this is always true. Whatever this number is, I'm going to have n of A and n of B. So I can take an A and a B, put them together. Another A and a B, put them together. Another A and a B, put them together. I will have n groups of A and B. And in fact, I could even go more. I could have C to the n, D to the n. And then I would have A, B, C, D to the n. But all you need to remember, this is just the extension, right? If this part is true, if this is true, then the bigger one is true. Because then I just say, okay, this times the other one, right? C, N, D, N. I will get C, D, N. And now again, I have two things to the power n, and so I apply the same rule. Right? Right. Now, you need to know these rules, and you have to be able to use them to simplify expressions. In calculus, we deal a lot with powers. So that's why we're taking time to make sure we understand how we work with powers. Otherwise, you're going to find calculus hard, not because the calculus is hard, but because the algebra is. You're not comfortable yet. So we want to make sure we're comfortable with the algebra so that it doesn't get in our way later. Let me check on time. 10 more minutes. All right, so let's do logarithms quickly. We'll leave this up on the board. We'll add that one down here. A to the n, b to the n is a, b to the n. Okay, so you had this question. If you're given 2 to the power x is a quarter, how do you find x? So a logarithm is written like this, log, and we have a base, sorry, no, not the base goes there. The base goes down here, and we have a number m, and we're looking for n. The way this works is b to the power n equals m. If this is true, then this is also true. So a logarithm is a different way of writing a power, basically. It's not a very sophisticated, funny, weird thing. It's a different way of writing a power. So now we say, the way I think of it is, if I have a base b, and I want to reach the result m, what is the exponent of b, what is the n that will give me this result? All right? So if I have 2 cubed is 8, that's true. Now I could write the logarithm of 8, and you have to give the base. By itself, this doesn't mean anything. You have to say in base 2. And that will be equal to, so this is okay, 2 raised to what power will give me the answer 8? 3. Yeah? That's all a logarithm is. It's sort of an alternative way of thinking about or writing a power. But it allows us to then solve equations like this. Because now, notice something. If I have the log base 2 of 2 to the power 3. So this is, I can write 8 like this, right? Then the answer is 3. But let me ask you, what is the log of 2 base 2? So let's think about it. If I have a base 2, right? So if I have a base 2, and I'm looking for the power, what should go here? What should go in the box? That it gives me the answer 2. What goes in the box? 1. Very good. 1. This is 3 times that, correct? Correct? So this is also equal to 3 times log base 2 of 2. The 3 came out in front because this is equal to 1. So 3 times 1, it will give me 3. I'm going a bit fast, I know. So you may want to read back through the book about the section on logarithms. That's the definition of the logarithm. Let me move that up here, just so we have a bit more space. So, so here's one rule. A logarithm base b of m or some number x to the m equals m log b of x. If there is a power inside the logarithm, that power comes out and multiplies the rest of the logarithm. And this is the feature of logarithms that lets us solve these equations. It's this power, this characteristic of logarithms, that we can use to solve that. How do we use it to solve that? So we have 2 to the x is 1/4. I'm going to write quarter over here. We'll see why in a moment. 1/4. Okay. It's not the easiest example, but it's also not hard. Now we know that if we do something to one side of an equation and we do the same thing to the other side, the equation remains true, right? So I'm going to take the logarithm base 2 of this and the logarithm base 2 of this. I use square brackets just to make it clear. I could have used these brackets. Doesn't make a difference. Now, with my special rule, the x can come in front. So this is x log base 2 of 2 equals log base 2 of 1/4. What is log base 2 of 2?
1.
Is 1. Mm-hmm. So this will equal 1. What is log base 2 of 1/4? My suggestion when you're refreshing yourself on working with logarithms is to, somewhere else on the side here, just write, okay, 2 to something equals 1/4. what is the something that gives a quarter, right? This is the same as this, right? Do we know what goes in here? 2 is close, not quite. Not -1. Not 1. 2 to what power gives a quarter?
Oh,
Negative.
-2, right? -2. So this is -2. Okay, so x times 1 is x. And this is -2. And I have my answer. I have solved from this. I got the answer, x is -2. Cool. All right, we're going to stop there for today. There are some other rules of logarithms that are listed in the book. I could write them down. Maybe I should. Is there, oh, let me make space down here. So, almost done. Log base b of, let's call it m, plus log base b of n is log base b of m times n. All right, this is inside, this is the logarithm of m times n. Right, so if you're thinking this is b to a power equals m times n. That's what this is saying, right? And similarly, the log base b of m minus the log base b of n is the log base b of m divided by n. I will leave it to you as an exercise to try to prove why these two laws are these laws. Try to show, like write the steps. Maybe start with some numbers to give you an idea, and then see if you can figure out the general rule. Can you show why this is true? So like we did with this one. When I said an bn equals ab to the n, and I showed, because if I do this and I move them, then I can always group them again, and therefore this is true. So I showed the steps of this is always true. So try to do the same thing for these ones. Okay? So your problem set will be what is it? Section, this is, what section is this? Chapter 2. There's a, oh, where is it? Come on. Oh yeah, did this turn on? No, it's still alive. Great. So there's a summary of this section. This is section 2.3. So there's a summary at the end of the rules of indices. Oh, we didn't do the fractional powers. So the other one that I didn't show here is, put it up here, b to the power 1 over n is the nth root of b, and b to the power n over m is the mth power of b to the n, which is also the mth root of b to the power n. It doesn't matter if you put the exponent inside or outside. So we didn't, this is discussed very nicely in the book, so you can find the pages for that. Everything we have done is in section 2.3. And then the rules, these are the rules of indices. Oh, we didn't show this one. That's also an important one. And then there are the rules of logarithms, which I just wrote down. So exercise, your problem set is exercise 2.3, except number 5. You can skip number 5. If you want to read that part of the section and do it, fine, but it's not required. You don't need number 5. I think everything else is fine. Yeah. And so there's 2 word problems at the end. And read them carefully. Yeah, so when this says, estimate the number of complaints received by the company each month for the first 6 months of trading, what are you asked for? Or more specifically, how many things are you asked for? How many numbers do you have to find? So you're asked to estimate the number of complaints. Okay, somehow there's a way to find the number of complaints each month for the first 6 months. That means you should have how many answers? 6. All right? And then you plot a graph. And then the next one, let me just comment. So 2 firm, this is giving you some information. Find the non-zero value of L. So now this is what I have to do. Find the value of L. The non-zero value of L means L could have the value 0, but we're not interested in the value 0. So there's another value of L, which produces the same level of output for these 2 firms. So in this problem, we have 2 firms, A and B. And they use the same labor input, L, and their output in the short term is given by QA is 108 times the root of L, and QB is 4L squared. So the question is, what value of L will make QA and QB equal? If they have the same level of output, then their output, QA and QB, should be equal. Right? So you take this, equal this, and solve for L. That's what this problem is asking. So there are 14 problems in this exercise. If you take out number 5, I think it was. Yeah, I said skip number 5, then there's 13 problems to do this week. I will send it to, I emailed it to everybody. So give me your email before you go. Yeah. Okay. Any questions? It's getting a little more exciting, a little more heated. Somewhat? Plain paper? Plain paper. Then you have to buy more paper. Math courses need a lot of paper. Okay.